horizontal bands going a jet in one direction, a jet in another direction, a jet just alternating eastward and westward jets. And you have some features. You see these dots here are vortices within these jets. And here is the biggest of all the vortices on Jupiter. It's the Great Red Spot. This is again a picture that was made by Voyager 2. And this is a huge vortex. This is twice the diameter of the Earth from one side to the other. And it's very turbulent, very irregular, but there is structure here. And I said that these structures can persist even very far from the uniform state and for very long times. This has in fact been observed for many years. It was first observed by Robert Hooke in 1664 in the very first issue of the first scientific journal, the Philosophical Transactions of the Royal Society of London. And I like this. It gives accounts of the undertaking, studies, and labors of the ingenious and the many considerable. And there's a report in this journal. It's not just Mr. Hooke, it is the ingenious Mr. Hooke. So he observed this spot in the biggest of the three obscure belts of Jupiter on the 9th of May, 1664, 9 p.m. So we set about to see if it might be possible to produce some of the features that lead to vortices and jets on planets. And if we look back at Jupiter, we see we have these strong jets, and we know, of course, the planet is rotating rapidly. The flow is turbulent. It's very irregular. So we make an irregular flow, a turbulent flow, in a tank which rotates very rapidly. And the tank is 1 meter in diameter. So it's 1 meter across here. And we pump fluid into the tank through these holes. So this has nothing to do with the fluid. And we'll visualize the flow by putting dye into the fluid. And you can see here there are two vortices that are rotating, and they have spontaneously formed. We haven't injected them or put them in. They've just occurred. And at some later time, these two vortices approach one another, and at a later time, 4 seconds later, they are starting to merge, and you finally end up with one strong vortex. And that vortex you can see in this dye picture. You can also see here in this picture made by suspending particles in the fluid and taking a time exposure. So the streaks indicate how fast the particles move, and you can see this large vortex here. This is a robust vortex that persists like the red spot persists. Even though the flow is very irregular, you have many vortices here, and vortices are shed from this one, and vortices are absorbed by this one all the time, but it persists. Well, I want to change the subject to another problem, which is a little closer to home. When you remove oil by pumping it out of the ground, out of the sands in the ground, the oil must be replaced by something. It's replaced by water. Now, if you keep pumping, after a while, you start pumping water, but a lot of the oil is left in the ground. And we want to understand why so much oil is left in the ground. Why can't we pump all the oil out and just leave the water down there? So we have a system which consists of two thick plates. These are actually blanks for a telescope. They're 1 foot in diameter here, but there's a thin spacing between them. It's just the spacing between the plate is very thin, about the diameter of a human hair. And we look down from the top at the thin oil layer contained between the two plates. Now, we inject air or water, doesn't make a difference, into this oil layer and pump out the oil, and the air replaces the oil. Now, if we pump slowly, we get fingers of air. This is looking down from the top, so you can see the air is making these fingers into the black oil here. We get these large fingers of air, but instead of the oil coming out uniformly, the bubble just growing in size, it makes fingers. If we pump out faster, we get more fingers. And if we pump out even faster, so here the oil is actually black, so the colors have changed. The oil is white, and the air is that little black dot there. And now we're going to pump out the oil and watch the air or water replace the oil. And you see you have a very complicated structure because these fingers of air split repeatedly, making this complex structure. And if you had an oil well sitting up here, you would be pumping out, say this was water, you'd be pumping out water and leaving all this oil. Okay. So we'd like to understand this kind of structure, and we've been studying it and find that unlike area, which is two-dimensional, or a volume, which is three-dimensional, or a line, which is one-dimensional, this has a dimension. It's called a fractal. It has a dimension which is not an integer. It's 1.7. Now, there's a mathematical model, a very simple mathematical model that looks somewhat similar to this, and it also has a dimension of 1.7. And we've also done some experiments on electroplating, not the smooth electroplating which you normally would want if you were plating silver or something, but for some conditions of the current and the concentration of the electrolyte, you get an irregular structure which has the same dimension. Well, that's just one number characterizing the geometry. We're in the course of studying other numbers to characterize the geometry here, and we find that in the latest work that these have the same properties, geometrical properties. So we understand something about these different structures, or have a mathematical description which is the same for structures which are quite different in the molecular origin. If you take a dish of nutrients on a gel, a petri dish, and inoculate it at the center with some bacteria, the bacterial colony will grow, and it won't grow as a circular ring of bacteria that grows in size. For some conditions, you get bacterial growth looking like, at least superficially, like these other structures. Whether it's quantitatively the same type of mathematical, has the same type of mathematical description, we don't know, but it's something that will be studied to determine. If you look at lightning in a breakdown of air or some material, this is work done in Switzerland, you also find that the dimension describing this is 1.7. Now that's just the geometrical properties. And we could also study how these different systems grow, how they change in time, and what is the characterization of their growth processes. And that's work that is ongoing to see if we can find a common description for very different kinds of processes, which is what one always seeks in physics, to describe a large number of phenomena through one central idea or one concept which you can explain mathematically. And certainly there are many different kinds of growth phenomena that look similar but have to be examined in detail to determine whether they really have the same underlying mathematical structure. And ultimately, we'd like to look at something like tumor growth. So, as I've described, if a system is driven from the uniform state sufficiently far, it will spontaneously form a pattern at a critical value of the parameters controlling the system, like the pattern in the surface of water that's vibrating, or these patterns in sand, or this is looking at a convecting fluid not from above, but from the side, where you can see that the heat rises here and falls here. So this would be hot on the bottom and cool on the top. These are the convection cells. This is the vibrating cornstarch. And this is a chemical pattern. So we can see that we have some reasonably good understanding of how patterns first arise, but there's much to be done when you push a system far from the uniform state and try to understand some of the complex problems we face in nature and in technology, where the systems are pushed very far from equilibrium. But we see in various situations common structures like spirals here, and the study of these structures through laboratory experiments and through computer modeling and through theory are leading to some unifying principles that help us understand a variety of phenomena, and hopefully we'll be able to address some of the more complicated issues in the future. Thank you very much. So if there are questions, I'll be happy to attempt to, yes, sir?
On the previous slide, could you explain
Uh, I could, but I don't think. If you cover this with small boxes and see how many boxes are necessary to cover this, and vary the size of the boxes as the boxes become smaller and smaller, and you look at those boxes which have some piece of the structure in it, and only count those boxes, and look at the way the number of boxes scale with the size of the box. From that, you can get the dimension. Okay? We can talk about it later. It's straightforward, but without a blackboard. Yes, sir. There was a question right here.
It's not a spatial dimension. It's some other kind.
Yeah, it's a spatial dimension. A square in a sheet of paper would have dimension 2. Okay, it would fill the space. Volume, a cube, would have dimension 3. This is something that has dimension less than area filling square on a piece of paper, but more greater dimension than just a line. Okay. The coastline, here's another way of thinking of it. This was done by Richardson in 1927. He was first to think of this idea of fractal dimension, one of the ones who thought of it. That if you look at the coastline on a map of a country, and you calculate the coastline with the length of the coastline with a ruler, you measure it, and it's a certain length, 2,000 miles. Now, if you make the scale on your ruler that you use to calculate that length smaller, you get a longer length, right? Because you're going in inside the bays and the crooks and crannies. And if you make it smaller yet, you get a longer length, and it keeps going up. The length increases as your scale decreases, okay? And you look at the way in which that length increases as your scale decreases, and you can determine the dimension of a coastline, which is 1.27, okay? Yes?
The second law of thermodynamics, it assumes basically the motion of particles is random. And every power plant I've ever heard of essentially does everything it can to improve on that principle, that motion of particles is random. And that seems kind of inefficient if you compare it to what we might be capable of if we took advantage of the way fluids like to move, if you'll excuse that loose terminology. One of the things you mentioned down there was an energy, and it seems to me that that might be one of the best applications of this sort of technology.
Okay. Well, the efficiency of a power plant or engine has an upper bound. It was understood many years ago by Sadi Carnot, a Frenchman,
Right.
whose work was almost lost until it was found by Lord Kelvin, William Thomson. Okay? He found this tract that was privately published by Carnot in 1827, and few people read it, and fewer yet understood it. But Kelvin did, and Kelvin really realized that this was an important step in understanding understanding the second law of thermodynamics and understanding how efficient engines could be. And that provides a fundamental basis for understanding the limit of efficiency of engines. Okay. You have more in mind. Okay. Let's take it. Yes. Can you speak louder, please?
You've mentioned several times a critical value for the parameter beyond which you see the emergence of order.
Yes.
What do you know about that critical parameter, that critical value, and how does one arrive at it? Do we know anything, or is it simply empirical?
No. Yes. If you start with a system that's uniform, and then you impose some difference across the system, a temperature difference or a velocity difference, as you increase that difference, the system will stay uniform or in the same state, but just distorted by having a temperature gradient, but still uniform with no pattern until you reach a critical value. And you can calculate that critical value by the technique that was used by Taylor and Alan Turing, and the general technique I described of solving for the uniform state and considering then what happens when there's a small disturbance. Does that disturbance grow or does it die? And at a certain value for that difference across the system, that critical difference, the disturbance, instead of dying, will start to grow. And you can given a system, if you know something about the system, you can solve for its uniform state, and then you can calculate the critical value of the parameter at which a pattern would form. Yes. Yes.
Can you say more about tumor growth?
No. Can I say more about tumor growth? No. Short answer. Yes.
So was the cornstarch that was vibrating, was that in real time?
The cornstarch pictures were in real time. The chemical spot pattern was sped up a factor of 30. That was not real time. That was sped up. But the cornstarch was real time. You can come to the lab and look at it.
When you're a young person and you look at the universe and think about whether there's a God or not, you look at evidence for intelligence in the universe, and the evidence that your grandmother tells you is look at all the patterns. And I take it from what you've shown is that these patterns come out of chaos, and that they're not a property of any kind of intelligence. The math is our own superstructure.
These patterns arise according to the laws of nature, like Newton's laws. Okay. Yes, we have an understanding of pattern. I mean, I'm not saying where the laws come from. That depends on your own belief system. Okay? We don't say, as scientists, you don't say why F equals ma, but that's the way it is. And that's strongly supported by many experiments. Or why does Einstein's theory of relativity hold? That is a description of nature found to be valid through many experiments, and we validate it by enough experiments to the point it's called a law of nature, okay? Or a theory. Yes?
Are most of these images and videos available already online? I'd like to share some of them with my students. Would it be possible for me to do that?
Yes, the papers are all online, and the movie, for example, the cornstarch movie, is, you can download it. When we put the cornstarch movie on our website a couple of years ago, here's the website. When we put the cornstarch movie on our website 2 years ago, we had 50,000 downloads in the first 24 hours. Okay, well, thank you very much for coming. I appreciate it.